In this section, we will see one efficient way how to compute a determinant. Let's start with the following example. Consider a matrix, say 30 by 30. A square matrix with just 30 columns and 30 rows. I guess such a matrix would fit on this blackboard. And we want to compute a determinant. Using the definition from the previous section, we could choose one row or one column, and we can expand the determinant along this row. So the number of operations would be roughly 30 times, because we want to evaluate 30 determinants. Each of them 29 by 29. For each of these 29 by 29 determinants, we again expand the determinant along a given row or some column. And for each of them, we want to perform 29 times the determinant of a matrix 28 by 28. And each determinant of this small matrix can be evaluated by expanding along a row or along a column, and we want to evaluate 28 determinants, each of them 28 by 28. And in this way, we need the number of operations to be 30 factorial. 1 times 2 times 3 times up to times 30. Well, what could be the time to compute this? Considering today's typical computer with the clock speed, say 1 gigahertz, the time would be so such a computer may perform approximately 10 to the power of 9 operations per second. Imagine we take a computer which has 1 million processors. So we can multiply by 10 to 6. So the time would be 30 factorial divided by 10 to divided by 10 to 9 plus 6 is 15. So this is the number of operations. This is the time, and we divide by the number of operations per second. So this is the time in seconds. If we divide by 600, we get the time in hours. If we divide by 24, we get the time in days. And if we divide by 365, we get the time in years. And when we compute this, we get something like 10 to 10 years. But this is approximately the time, the age of the universe. So to compute the determinant using this definition, expanding by a given row, even for not too large matrix, is completely unrealistic. So this is time to develop another method. And a much more efficient method to compute determinant is to convert the matrix to the upper triangle form. Because if we have a matrix in the upper triangle form, say 2, 7, 15, 0, 3, 2, 0, 0, 5, you see in the upper triangular form means that below the main diagonal we have only zeros, while and on the principal diagonal there are zero numbers. If we now expand this determinant along the first column, we get 2 times this subdeterminant plus 0 times something plus 0 times something. We don't have to write these terms because they are 0. And this subdeterminant can be again expanded on the first column, which is 3 times this subdeterminant. And this is just 5, the number. And this works even for larger matrices. So we see that the determinant of a matrix in the upper triangle form is just a product of the entries on the principal diagonal. So just n operations instead of factorial. Well, and what is the number of operations to bring the matrix to the upper triangle form? To get this 0, we want to operate this row. One row has n entries. But we want to clear not just this number, but all of the first column up to the topmost element. So instead of one row, we must consider roughly n rows. So we have n square operations to clear the first column. But this is not the only column in the matrix. There are n columns. So very roughly speaking, we have n cubed operations necessary to perform to bring the square matrix into the upper triangle form. But this is much less than n factorial.